Hi, welcome to All Measurements Have Uncertainties. So in this video, we'll be talking about measurement uncertainties, or in other words, error bars. We'll be trying to cover two basic topics. First of all, the concept that all measurements have uncertainties. And second, types of uncertainties and how they arise. You might want to check out the video Why Measurement Uncertainties Are Important, also available on this channel. So here we'll be looking at some sources of error in everyday life. This introduction to measurement uncertainty will be at a very basic level. We'll save more precise mathematical statements for other videos. With that, let's look at some examples of uncertainties in measuring speed, time, and distance. Okay, so let's do the first example. So let's say you're pulled over by a cop who says you were driving 72 kilometers per hour in a 50 kilometer per hour zone. Now, you weren't going exactly 72 kilometers per hour. Maybe you were going 72.1624, etc. kilometers per hour, or maybe 71.959, etc. kilometers per hour, or maybe you were going 72.433, etc. kilometers per hour, but you were not going exactly 72 kilometers per hour. Okay, let's look at another example. So let's say you look at your watch and it says 3:47 p.m. A little while later, you see that it says 4:13 p.m. You conclude that 26 minutes passed in the interim. Now, it hasn't been exactly 26 minutes. You haven't taken into account fractions of a minute in your start and end times. And also, your watch isn't perfectly precise, so your 26-minute estimate has an error bar. Let's look at yet one more example. So let's say you want to measure the dimensions of a box with a ruler, and the smallest gradation on your ruler is 1 millimeter. So you probably won't be able to measure the lengths of the sides of the box to a precision much better than 1 millimeter. We can also look at more subtle examples. So there are even error bars on statements we make that don't contain numerical values. For example, we might describe tiles on a floor as square. Now, are they perfectly square? No. If we measured the lengths of their sides precisely, we'd find that they weren't the same, and their corners wouldn't be perfect 90-degree angles. As another example, we often say that the Earth is a sphere, even though it's squished at the poles and it has mountains. So here we're using idealized models. We treat the tiles as square and the Earth as round within some margin of error. So these examples illustrate a general and important point. All measurements have error bars. So uncertainties are everywhere. Does this mean that we really don't know anything? No, but we should know how large the uncertainties are and whether they are small enough for the application we want to use them for, and whether or not they affect our conclusions. Also, if measurement uncertainties are everywhere, and if they're so important, why aren't we constantly quoting uncertainties in everyday life? Well, when we don't quote an error, we're assuming that the error is small enough that it doesn't matter for our purposes. This might be because we simply don't need a very precise answer, or maybe it's because other uncertainties are much more important. So let's look at an example. So let's say that you plan to drive to some destination and you want to know how long it will take. A friend tells you that the trip is 50 kilometers. And let's say that the distance is actually 52.3 kilometers to 3 significant digits. Why might you not be bothered by the imprecision? So let's look at a couple of possible reasons. First of all, maybe you don't have to be at your destination exactly on time. So in this case, you don't need a very precise answer. Or maybe you know that the unknown traffic conditions will have a much larger effect on the trip duration. So in this case, other uncertainties are more important than the 2.3 kilometer distance error. On the other hand, if you're using distance markers to figure out what exit to take on the highway, the difference between 50 and 52.3 kilometers might be very important. The important thing is to know what approximations are okay for your situation. Okay, so far we've introduced a few everyday examples of measurement uncertainty. We concentrated on cases where your measuring instrument has a finite resolution, like the gradation on a ruler. There are also other types of uncertainties which we'll now look at: statistical, systematic, and theoretical errors. So let's start with an example on statistical errors. For this, it's useful to study a familiar event that happens at irregular intervals. You may know about the hobby of plane spotting, watching airplanes take off and land at airports. But planes take off and land on schedules that are way too reliable for this example. Luckily for us, and perhaps incredibly, bus spotting also exists, so this example will be about that. So let's say that you're at a bus stop. You know that the buses leave their origin every few minutes at equal intervals, but you don't know what that interval is. Some buses get delayed due to traffic, while some make it through faster than expected. So the buses don't arrive at your stop at regular intervals. They arrive more randomly than that. But you want to know how often buses leave their origin. You decide to count the buses arriving in a certain time interval and divide the interval by the number of buses to estimate how often they leave the depot. So you measure for 5 minutes, and one bus stops by. Does this mean that the buses leave the depot every 5 minutes? No. Maybe the buses only come every half an hour and you just got lucky. Or maybe they come every 3 minutes and you just missed one. You need better statistics. So you do another measurement. You measure for an hour and 5 buses stop by. You estimate that buses leave the depot every 60 minutes divided by 5 buses equals 12 minutes. Now this estimate is better. It's now looking unlikely that buses run every 3 minutes, which would have resulted on average in 20 buses passing by per hour, or every 30 minutes, which would have given 2 buses per hour. Now, if you're dedicated, you could observe for a long time. So let's say you observed for 100 hours and 613 buses came by. It's starting to look a lot like the buses run every 10 minutes. So 6,000 minutes divided by 613 buses is 9.8 minutes. It's looking very, very unlikely that the buses run every 3 minutes, which would have yielded around 2,000 buses in 100 hours, or every half hour, which would have yielded 200 buses. So these estimates have different levels of precision. With a 5-minute interval, you might have 0, 1, or a few buses show up, and how many show up affects your estimate a lot. For a long observation time, you can divide the time into many 5-minute intervals. Some intervals will have a few buses, some will have 0, but the fluctuations tend to partially cancel when you add them all together. So, if you have very long observation times, the rate at which buses arrive at your stop should be very close to the rate at which they leave the depot. Errors like this, that depend on how much data you take, are called statistical uncertainties. And a nice feature of statistical uncertainties is that you can reduce them by taking more data. For more detail, you can check out Poisson statistics. The buses in this example won't exactly obey Poisson statistics, but it's a similar idea. There is a Poisson statistics playlist on this channel, which you might find useful. Now, let's give a couple examples of systematic uncertainties. First, let's go back to our bus example. Let's say that there are 2 bus routes that stop at your stop, the number 5 bus and the number 7 bus. You want to separately figure out the rates at which the number 5 and number 7 buses leave their origins. But let's say that 10% of the buses aren't clearly marked, and you have to guess if they're a number 5 or a number 7. This will introduce an error in your estimates of the separate number 5 and number 7 rates. And taking more data won't fix this. This is a systematic error. As another example of systematic error, let's say you're measuring the time between 2 events. Unfortunately, the only clock you have is old and not very reliable. Old clocks of this type are known to tend to run between 1% slow and 1% fast. This results in a systematic uncertainty in your timing measurement. Taking more data with the same clock won't reduce this uncertainty. A particular type of systematic error is a theoretical error. This is an error that doesn't come directly from an experimental procedure, but from a calculation. Let's say you're trying to figure out how much dog food you should give to your dog. So, the dog food bag says to give your dog 1 scoop, that's provided with the bag, for every 10 kilograms of body mass of your dog daily. You put your dog on a scale and find that he or she has a mass of 20 plus or minus 1 kilogram. So you conclude that every day you should give your dog 2.0 plus or minus 0.1 scoops of dog food. But your vet later tells you that the parameter value you used of 1 scoop per day for every 10 kilograms of your dog's body mass has an error on it. She tells you that it has an uncertainty on it of 20% because it depends on the type of dog and its activity level. A 20% error on your calculation of 2 scoops per day gives an additional error of plus or minus 0.4 scoops per day. Now, you had assigned an error of plus or minus 0.1 scoops per day because of the experimental error in weighing your dog. But the parameter which you used in the calculation introduces another error of plus or minus 0.4 scoops per day. This second uncertainty comes from an error on a parameter in a calculation and is therefore a theoretical error. Okay, so let's summarize. So all measurements have uncertainties, and here we've discussed a few everyday examples. In daily life, we casually use approximations and idealized models all the time. But the important point is to recognize them as idealized models and make sure that the model we're using is good enough for the situation at hand.